Hello all. Today we'll discuss the capacitor characteristics. Okay. So let's list out the capacitor characteristic that we are going to discuss. So first characteristics is the capacitance. Okay. Okay. Second characteristics. Okay. Rated voltage. Third characteristics ESR. Okay. Fourth characteristics is maximum continuous voltage. Fifth characteristics insulation resistor. Sixth parameter DC leakage current. It is also called residual current. And seventh characteristics is self-discharge. And eighth characteristics is dissipation factor. And quality factor. Okay. Then next is ninth characteristics dielectric strength. 10 is temperature coefficient. Or temperature dependency. 11th is pulse rise time. 12th is pulse loading capacity. 13th is dielectric absorption. 14th is ripple current. Okay, so this is all the list of the electrical parameters we'll discuss of capacitors. Okay, so in case if you haven't heard of any of these, don't worry, we are going to discuss all of them in detail. Okay, so let's start from the capacitance. So our first topic is capacitance. Now, as we know, the capacitance is the most important property for the capacitor. So, what it defines? It defines the ability to store the charge, ability to store the charge. Condition is for a given voltage. Okay, so capacitor. Another way we can say it denote how many units of charge can be stored in capacitor per voltage unit. So we can say also how many units of charge can be stored in the capacitor per voltage unit. So let's understand it. We know Q is equals to CV. Now, if we further simplify it and we equate C is equals to Q by V. So, let's say if I make potential difference for 1 volt and it stored 1 coulomb of charge, then it defines 1 farad. Now, farad is the unit of the capacitance. Okay. Okay. So also we can define as now Q, further Q is equals to I into T. Now if I further simplify this, I can say 1 amp per second divided by 1 volt defines 1 farad. So let's say I have one capacitor and I have applied 1 volt across it. Okay. Now if it stores 1 coulomb of charge, then I say 1 coulomb by 1 volt per unit volt, we can say this is a 1 farad. Okay, and in case so now let's say I have capacitor, I have applied 2 volt and it stored 8 coulomb of charges. So 2 volt and divided 8, not 2, 4. So per unit volt it stored 4 coulomb of charge. That means the capacitance value is 4 farad. Or another way we can say if I have a capacitor, now it has 2 volt and I have attached some circuit and this capacitor is 4 farad. Okay, so I can say this capacitor can provide total Q is equals to C into V. So C is equals to 4 and V is equals to 2. 8 coulomb of charge with the expense of 2 voltage. That means After providing 8 coulomb charge to a circuit, this capacitor will exhaust all the voltage 2 volt to 0 volt. So your provided capacitor is able to provide 2 coulomb of charge, but is not a free of cost. Its expenses is dropping 2 voltage to 0 voltage, or is exhausting all the voltages, potential differences. Okay. So or further we can say 8 coulomb, if I say 8 amp for, if I say 1 second, for 1 second it will be able to provide 8 amps current to this circuit. Or if I say 4 amps for 2 second, or 1 amp for 8 second. I hope now you understand what is the meaning of this Q is equals to CV or capacitance. Okay, so let's go forward. Now, so first we discussed first parameter capacitance. Now we look into the second parameters, that is voltage. So how capacitors influenced with the voltage. Now, particularly for ceramic capacitor, if we apply the voltage, if you look at the voltage versus capacitance graph in terms of percentage, you'll be able to see these graphs falls with the applied voltage. So if you apply more and more voltage, your capacitance will more further reduced. So this effect is called DC bias effect. Now let's say you have 47 microfarad capacitor with 25 volt. But when you apply 20 volt or 25 volt, this capacitor will no more be 47. It might be 35, maybe 35 microfarad. Okay, you need to check in the manufacturer data sheet how much percentage is getting derated. So this effect is mainly very significant for the ceramic capacitors. It, this capa but for all other type of capacitor, film capacitor, electrolyte, this effect exists but not significantly like ceramic capacitor. Third parameter we look, third effect is a sub effect, we can say dependency on the, sorry, 2.1, I rather say 2.1. Frequency. Okay. So same sort of characteristics also seen with the frequency. Okay, so with applied frequency, if we apply more and more frequency, it has been seen that capacitance get reduced. There are other factors too which can influence the capacitor characteristics. Okay, so if I see 2.2, that is dependency on time, like capacitance gets changed over the time due to aging process. Okay, so if capacitors are being used for a long time, it has been seen that the capacitance got reduced. maybe like 100 microfarad capacitor no more behave as a 100 microfarad capacitor, rather it become 80 microfarad capacitors. Okay, so if you look at the if I plot the graph operating time in hours and the capacitance change, you'll be looking that it is further decreases over the time. Okay. There are another things like 2.3 I keep tolerance. So the capacitance tolerance, what it denotes that possible positive and negative deviation from the nominal capacitance. Let's say you have a 330 microfarad capacitors, but 330 microfarad is all. It's not 330. There will be plus minus variation. Will be always exist. So it may be 25% more or maybe 25% less. That will be defined by the manufacturer. Okay. So this capacitance tolerance is measured and specified by manufacturer at a particular standard temperature, usually plus 20 degrees Celsius. Sorry, plus 20 degree Celsius. Okay, and this test has been generally performed at very low voltage. Okay, now there is another important note. It should be pointed out that the capacitance tolerance is only ever defined as a possible deviation from the capacitance at the time of delivery and does not apply for the entire period of use of product life of capacitor, because there are other factors also influence the capacitance changes. Okay, just like we have discussed, one of the parameters, aging. Okay, so, our third parameter will be SR. So it's called equivalent series resistance. Now generally we have studied in our school the capacitors looks like this, but this is the ideal capacitor. A real capacitor is different. Let's see how it looks like this. It has some inductance, it has some resistance, and then it has capacitance. Okay, and sometimes you see there is another resistor, parallel resistors across it. This is called leakage resistance. Its value is comparatively very high. This is called ESR and this is called ESL. Okay. So it's quite complex. It looks like it doesn't look as simple whatever studied in the school. So this is the equivalent circuit of a capacitor. So there is or is this all the another name? This is called insulation resistor also. Now the importance of insulation resistor is the capacitor self-discharge happens through this insulation resistor. Now a higher quality dielectric leads to an increase of this resistance. Okay, and so it becomes apparent that high quality dielectric increases the possible capacitance. Okay, but the actual storage capacity of the capacitor also improves as the self discharge drops with increasing resistance. So now if you're increasing this R leakage resistance or insulation resistance, it goes higher and higher, self discharges decreases. Okay. Now the equivalent series resistance, this effective ohmic resistance exists between the connectors of the capacitor. So it combines all ohmic components. Okay, because if you look at the capacitor construction, there are foils which wrap around the electrodes. Okay, if you look at this type of foils wrap around the electrodes. Now this foil has some finite resistance. So this is what basically ESR, and also includes contact resistance, while this red foil resistance. Okay, now so what is the significance? Now we'll discuss what is the significance of this ESR. Now ESR is a criteria. Basically we can say ESR is a criteria for how well the capacitor passes alternating currents. How well the capacitor passes alternating currents. Okay. So the ESR can be determined for a specific capacitor from data sheet. In case if it is doesn't if not mentioned, generally manufacturer mention the ESR for particular frequency, right? Yeah. But in case if it's not mentioned, you can find out from this formula tan delta divided by 2 pi fc, okay, or tan delta into xc. So we'll discuss regarding how what is this formula from where it is comes. We'll discuss in details. Now, not we also see the one more component, that is ESL. Okay, so this comes from the lead. Okay, now there are two types of capacitors generally by construction is available. One is leaded type. You will be seeing this is the capacitor and there's a two lead coming, and that is the SMD capacitors. Now this lead provides higher inductance. Now if in your design if you're very precise design and you don't want to this ESL can affect your design parameter. Okay, in case of high speed, if your design is high speed design, then ESL create a problem. Now you want like very low ESL capacitor, so in that case you can opt for the SMD capacitor. Okay, this ESL is almost half of the leader type. Okay, so okay, so let's say now in most of the cases we just ignore the insulation resistor or leakage resistance. So we can see this is a C, this is the ESR, and this is the ESL. So now we can see that we have to describe the impedance, because it will consider all these parameter resistors, inductor, capacitors. So because now we can't ignore, you can't simply write XC, okay, Z is equals to XC 1 by XC, or X equal to 1 by omega C. You can't simply write this formula. No, you can't ignore that ESL or ESR. Okay, so you have to take account all these three components. Okay, so in that case Z is equals to ESR plus XL minus XC whole square. Okay, so all this like this ESR, okay, and the capacitor XC and this XL, all of these three components are frequency dependent. And if you look at the graph, so this is XC, this is the XL, this is the inductive behavior, this is the capacitive behavior, and if you look at this ESR value also like this, and overall Z behavior is like this. Now, as it contains all the inductance, resistance, and capacitance, so definitely it will show the resonance effect. So, a practical capacitor doesn't show capacitance for all the frequency. Like if you look at this, it's so like this behavior. Okay, this is resonance frequency. Okay, so this is the capacitive component, and this is the inductive component. So if you operate your capacitors more than resonant frequency in this range, then a capacitor behaves as a inductor, and it behave and it act like an inductor, and you might get surprised why capacitors not behaving like as intended in the circuit, because you are operating your capacitor above the resonance frequency, and that is the reason your capacitor might not behave like a capacitor. So if you behave f less than fc or fr, that is the below resonant frequency, then dominant behavior, so capacitive behavior. Okay. And f is equals to fr, it was resistive behavior. So the mainly ESR will dominate, because here XL and XC cancel each other, and if greater than fr, it will show inductive behavior. So in case if you want to find out the resonant frequency for particular capacitor, you can find 2 pi root ESL into C. Okay. Whenever you go for the capacitor, you will look in data sheet and they will provide the frequency versus capacitance graph, or impedance graph, sorry, impedance graph. Okay. There will be looking like this type of curvature. Okay. So from there you can decide effectively whether your the selected capacitor and your frequency of operation region, whether it will be effective like capacitor or not. Okay. So let's stop today, and we'll continue with more many interesting facts of the capacitor in the next session. Thank you.